Welcome to 6.6, Solving Exponential and Logarithmic Equations. Our essential question today is how can we solve exponential and log equations? And for exponentials, we're going to convert to logarithms. If 4 to the x equals 17, then what does x equal? We can convert that over into log form in order to isolate x, so the log base 4 of 17 is equal to x. In order to solve this, we're going to want to change our bases. And intelligent bases to switch to could either be the common log or the natural log. With either one of those, grab a calculator and see that the answer is going to be slightly over 2. We can also solve log equations using exponents, and in this example, the log base 2.6 of x is equal to 3. If we convert that over into exponential form, we'll have x is equal to 2.6 cubed. Grab your calculator, and we'll find out that that's 17.576. In this lesson, when we're solving exponential and logarithmic equations, we are for the most part going to solve algebraically, but we can also solve graphically. So if we just take the first example of e to the x equals 2, a traditional way for us to solve this would be to bring both of those expressions to one side and say y equals, and then determine where does this function cross the x-axis. So we've taken e to the x and we've shifted down 2 units. What we're doing is seeing when does that function intersect with the x-axis, y equals 0. What's being suggested to us here is that we could just simply graph the left side and the right side and see where they intersect. So e to the x and 2, if y equals e to the x and if y equals 2, where do those intersect? You can check out the y equals 2 and realize that it's going to be on that horizontal line. And so when I look at that, I either am focusing in on graph C or graph D. Do you see that both of those have the line y equals 2 graphed? E to the x is exponential growth because the base is 2.7. So which one is it? Is it C or is it D? It's a little bit difficult to tell at the outset because they both go through the point 0, 1 for the y-intercept. They both intersect when y equals 2. So then we can go to another point. In point C, in graph C, do you recognize that when x equals 1, if we go up and see where that blue graph is intersecting, it's slightly under 3. Use your notion of E and realize that that's about 2.7. So we're going to be able to say that equation A matches up with graph C. So if we come down to D and realize that that must be a different equation, take a look at the 6 options. The only other one that has an equals 2 is equation F, 4 to the x equals 2. Look what happens in graph D when we come over to x equals 1, slide up until we come to the point 1, 4. Do you see that the blue graph is intersecting? So if x equals 1, the left-hand side of that equation is equivalent to 4. So I'm going to put in for equation F, it corresponds to graph D. Looking at those 6 graphs, we've taken care of the 6 equations, we've taken care of A and F. I'm going to turn my focus now to C, equation C, because notice that also is exponential, 2 to the x and 3 to the negative x, whereas B, D, and E are all logarithmic. So I'm going to focus in on C and realize that 2 to the x is going to show exponential growth. The only other one that shows exponential growth is graph A, and if I follow the blue growth there, I see we're passing through 0, 1. I also see that we're passing through 1, 2. That fits on the left. And on the right-hand side, when the equation says 3 to the negative x, that's going to be exponential decay. The red graph seems to suggest that. And if we go over to negative 1 for x, if x equals negative 1, do you see how the red graph passes through positive 3? That's a good indication that equation C is going to correspond to graph A. Okay, so now just going back up in order, if we look at log base the natural log of x equals -1 for equation B. On the right-hand side, -1 should be a line. Look at graph F. Do you see that that red line is when x equals -1? Take a look at equation D, the log base 4 of x equals 1. Which of our functions has a line of y equals 1? That looks like E. And then finally, equation E, log base 5 of x equals 1/2. Which has that line y equals 1/2? That looks like B. Check those out and just make sure that the left and the right-hand sides seem to make sense. Sometimes it's difficult to accurately graph e to the x or the log base 4 of x without a calculator, but you can find some key points. One of the most basic concepts of algebra is that in an equation, the left side of an equation equals the right side. If we can get the bases of exponentials to be the same, then it would stand to reason that the exponents have to be equal to each other also. It's not quite so easy all the time as just setting up 3 to the x equals 3 to the 5, so x equals 5. But if we can change the bases so that they're the same, then we'll be able to look at the exponents a little bit more easily. Let's use this property to solve for x in each of these three equations. When we look on the left and the right, we see that we have two equations with bases of 5 and bases of e. Let's solve these two things simultaneously. Our property tells us that if the equation means the left and the right-hand sides are equal and the bases are equal, then the exponents have to be equal also. So we can take 3x plus 1 and set it equal to x plus 17. And on that right example, we can also take 7 and set it equal to 2x plus 1. Now all we need to do is subtract the x to the left, subtract the 1 to the right, subtract the 1 to the left, do a little bit of division, and we come up with either x equals 8 or x equals 3. Go ahead, plug back in. If x equals 8, we're going to have 5 to the 25th equals 5 to the 25th. Just confirm that that's true. And we'll also have e to the 7th is equal to e to the 2 times 3 plus 1, to the 6 plus 1, e to the 7th. When we look at that middle example, the difficulty is that we don't have equal bases and we don't have equal exponents. But I do recognize that we can do something with that 9. We can express 9 as 3 squared, and now the equation holds up where the left and the right-hand sides are equal, the bases are equal, and so 5x is equal to 2x plus 6. Once we set those equal, we can subtract 2x over to the left and get 3x equals 12, divide by 3, and we should have x equals 4. Again, if you plug that 4 back in, 5 times 4 is 20, and 4 plus 6 is 10, but 9 to the 10th is going to be the same thing as 3 to the 20th. Or if you want to say 2 times 4 is 8 and 8 plus 12 is 20, then we can also say that that second row has exponents that are equivalent to one another. Let's bring that concept into example A. Can we solve the equation 1000 to the x equals 1 over 100 raised to the 2x minus 1? I hope it doesn't take too much effort to recognize that 1000 and 100 both can be written as 10 to some exponent. So when we rework this, do you see that the left side can be 10 cubed raised to the x, and 1 over 100 could be 10 to the negative 2. Our power property says that we can multiply those exponents, and now the left and the right hand sides of the equations are equal, the bases are equal, so doesn't that mean that the exponents have to be equal? Add 4x to the left, divide by 7, and we get our value of x. On the right hand side, it's not quite so easy. How can we convert 9 and 15 to have some common base? That's not going to be quite so easy, but we can use logarithms to help us solve exponentials. So let's come up with some common base. Let's come up with whatever base we want. How about e? The log base e of 9 to the x equals the log base e of 15. Remember, what you do to one side of the equation, you can do to the other. So we're just applying the logarithm to both sides. And now the power property says that we can take that x and we can bring it out as a coefficient. So x times the natural log of 9 is going to equal our right side. Notice that I've converted from log base e to just shortening it to the natural log. And that's x times. We can undo that through division, and we can figure out what our approximate answer is. It doesn't always guarantee that we're going to have rational answers, but we change the base, whether that's easy to come up with, such as 10 over on the left, or if we have to use logarithms and come up with whatever base seems to make sense, we still work with getting the same base to be on both sides, and then we evaluate. One pretty cool application to exponential growth and decay is Sir Isaac Newton's law of cooling. His formula here is chock full of T's and R's. It can be a little bit confusing, so let me try to flesh it out before we get started with using it. First of all, the T is equal to the temperature of whatever the item is after time t. So if we take something hot off of the stove, it's initially, let's say, boiling at 212 degrees, and then it's going to start to cool down. Well, what is the temperature after 5 minutes, 10 minutes? That's T. The T sub 0 is the initial temperature. If it's boiling for 5 minutes or 10 minutes or an hour, it's holding steady at 212. That's the initial temperature. As soon as you take something off of the stove, now it's starting to cool. The T sub R is the surrounding temperature. You can think of the R as being room temperature. If you're going to take something that's boiling hot and put it into the refrigerator, then it's the surrounding temperature. What's the temperature inside the refrigerator? That's not the temperature of the room. Or if you want to put something outside, then it's the surrounding temperature. But if you think of room temperature, you'll get a pretty good sense of what that means. If we take that T sub 0 minus T sub R, that's the difference between the two. How hot was the original item and what's the room temperature? So what's the difference between those? And if we look at the e to the negative RT, first of all, remember e is equal to about 2.7. So if we find the inverse of that, that roughly equates to 0.368, which means it's going to be talking about exponential decay. The longer we wait, the more something is cooling off. The R is the cooling rate, and that's going to change depending on what the item is. A piece of ice is going to cool at a different rate than tea or stew or any kind of item that's going to cool down. Your skin, depending on what the item is, that R will fluctuate. So we'll have to be told what that R equals. And finally, T is time. And that's the time that something has been sitting and cooling. We had a tea kettle on the stove, it was boiling, we took it off, we poured the tea, and now we've been waiting for 15 minutes, that's tea. So just a quick illustration here. You can see that we're going to start off at some initial temperature, and as time goes on, the temperature of the item is going to cool down, but it doesn't mean that it's going to cool down to 0 to negative and going towards negative infinity. It's going to cool down so that it comes asymptotic with whatever that T sub R is. So let's take all of those T's and R's and apply them to this situation. You're cooking a special meal for your family. You pull something out of the oven that you had set at 315 degrees and you let it cool off for a while in your kitchen, which is currently 68 degrees Fahrenheit. According to the recipe, you should let that thing sit for a while so it cools down, and it's best to serve when it's 100 degrees Fahrenheit. How long should you wait to eat, provided that that rate of cooling is 0.045? So here's Newton's law, and let's plug in what we know. First of all, we want to eat when the temperature is 100 degrees, and the difference between when we took it out and room temperature, 315 minus 68, goes in the parentheses. Also, the 68 at the tail end says that it's going to be cooling off consistently as we get towards room temperature, 68 degrees, and our rate goes up in the exponent along with our only unknown here, time. A couple things we can do to simplify this. We can subtract what is 100 minus 68 and also what is 315 minus 68. So we get 32 and 247. And remember, when we're trying to solve exponential equations, we want to be able to isolate the exponentials, so let's divide 32 by 247, and we solve exponentials by switching over to logs. Here, the base of our exponent is e, so you know that we're going to want to use the natural log. The final thing we want to be able to do is get t by itself, so we're going to divide by that coefficient, negative 0.045, and I'm expressing that as multiplying by the reciprocal. I could have divided that natural log by negative 0.045. I just didn't feel like having a complex fraction. The logarithm of a quotient divided by something else. Also, what is 32 divided by 247? I don't know that right off the top of my head, but I'm going to hold on to those numbers because my equal sign is still accurate. I haven't approximated anything yet. Now it's time to do so, and when we do, we come out to about 45, a little bit longer than that, so we should wait about 45 minutes before serving. Have some conversation, have some appetizers, and enjoy your meal about 45 minutes after you take it out of the oven. Here's an example with an error. We have a log expression equal to 4, and if we were to convert over to exponentials, we could think of both the left and right sides of the equation as being exponents, and we could create bases. So on the left, they intelligently create 3 as a base, but they aren't consistent. On the right-hand side, they make 4 the base and put 3 as the exponent. It would make more sense if they chose to have 3 as the base for both. We have a property that says when we have 3 raised to the log base 3 of something, we are just simply left with that 5x minus 1, and 3 to the 4th equals 81. From there we can go and solve to see that our answer comes out to 16.4. Another way to think of this is to just convert that log equation into an exponential by saying 3 to the 4th equals 5x minus 1, and then you can simply follow from there. Very often the use of logarithms comes into play when we want to solve the question of when. How long will something take? Because so often in our functions, one of the variables in the exponent is time. And that's the situation here as well. Excuse me, if we knew the age of the shark, we could plug in that value of t and we could predict its length. But more often than not, we're going to come upon a shark, we can measure its length, and then we can predict its age. So to do that, it might make sense to first try to isolate t. So we can subtract the 266, we can divide negative 219, and at this point we have that quotient on the left equals e to some power, so convert over to log form. Now the only thing left in order to isolate t is to divide by negative 5/100, or the reciprocal of that is to multiply by negative 20 equals that log expression. And now we have it so that t is isolated. We happen to know that in this particular case, the shark is 175 centimeters long, so we can insert that value, perform the math, run a calculation, and the shark is about 17.6 years old. Thank you for watching, everyone. Hope you have a great day. Your homework will be posted. Ask questions as they come.